Good afternoon and welcome everyone. Welcome to our webinar, which is supported by the Program Management Unit for Human Resource and Institutional Development, Research and Innovation. So for this week, our speaker is Dr. Ramin Kersi. Dr. Ramin Kersi is currently a postdoctoral researcher at Chulalongkorn University. He earned a doctorate degree in chemical engineering from the University of Putra in Malaysia in 2018. And in 2019, he joined the Faculty of Engineering, Chulalongkorn University, Bangkok, Thailand. His expertise in zinc air batteries and electrochemical processes, his current research focuses on the modification, development, and optimization of zinc airflow batteries. In addition to his experience with numerical analysis, modeling, and computer simulation, he has conducted electrochemical analysis and electrode fabrication. So, welcome, Dr. Ramin, and now the control is yours. Thank you.
Thank you very much for your introduction, Professor Suratep. I'm very glad to be invited to this Chulalongkorn webinar series. I know that this series has been going on uh, since start of October, and it's a pleasure for me to be a part of this webinar series. Um, yes, as you correctly indicated, I've been working in the energy storage research group for almost 3 years, for more than 3 years by now. And in our research group, many of the members and colleagues are working, and uh, they are focusing on developing and improving the materials and components of zinc-based batteries, and also as well as the flow batteries. Um, so I'd like to share my slide, and I hope you can hear me clearly and see my screen as well. Mm. So my presentation for today is focused on the stabilizing zinc anode for rechargeable zinc air batteries. Actually, I believe upon the as stated several times in the literature, as well as on my experience, I believe that this the zinc anode is the bottleneck of the zinc rechargeable zinc batteries. So which limits the shelf life of the battery, and I will explain in detail in the during the slides. But today I'm going to cover the outlines of energy storage systems. I'm also going to briefly talk about the electrochemical batteries, and in particular the metal air and zinc air batteries. And I'm going to provide some information regarding the obstacles for zinc air batteries in order to commercialize. So in order to be able to explain that, I'm going to review two of uh, our recently published papers. The first one is a review paper uh, that talks about the stabilizing zinc anode for different configuration of zinc air batteries, and the second is an analysis of parameter in order to optimize the zinc air battery, the flow battery. Uh, so in today's world, uh, the demand for energy has been drastically increasing. This is due to the progress and advancement of technology, and especially the availability of many electronic devices for nowadays, and also the pattern of the energy consumption has been uh, has is different from the previous times, and also uh, yeah, and And also, as you may know, that over the past few years, due to the pandemic, so that pattern of energy consumption also been deviated from the normal trend, and it is very hard to anticipate and also to forecast what is going to be the right trend in the future. So, therefore, it emphasized the role of energy storage systems, uh, and once they can benefit us in many ways. Like, first of all, we should consider that there should be a balance between the supply and the demand for the energy in the market. So, um, in case any like storage system are making it very easy and feasible for storage in case there is any excess energy has been generated, you can store it in energy storage equipments, and also while there is a shortage of energy, you can use those stored energy. And the other advantages that they provide is that once the renewable energy has been integrated in today's energy resources, they are we know that some of them are very unstable in providing the power outputs, like and for instance, if you want to generate energy from biomass resources, you may know that these resources, the current technology to operate this um, to use this source of energy are only efficient to about 40 to 50 percent, and so the output energy is also very unstable. So you need to store them prior to use them. You cannot directly use them. And the other thing is the continuous availability of the energy resources. Like for solar system, you're only able to capture and collect the solar energy during the daytime, but you cannot access to those energy during the nighttime. So it is very important that you are able to store this kind of energy before use. And energy storage systems are mainly can be categorized in, as it's indicated in the slides, but the most highlighted ones are the batteries, the supercapacitors, and fuel cells. Okay, moving to the electrochemical batteries, they are mainly categorized, or at least this, they can be categorized in sort of primary batteries, rechargeable batteries, and flow batteries. Primary batteries are those that are not rechargeable, and the kinetics are not reversible. And once you use them and discharge them, you need to discard them, and you cannot use it anymore. Like the zinc carbon batteries, lithium batteries, mercury oxide, that you can find them easily in the market. The second category is the rechargeable battery. The most popular ones are lead acid battery, which they are being used in automotive vehicles, and also the nickel-based batteries, zinc-based batteries, sodium-based, lithium-based batteries, which they're in the among the room temperature lithium-based batteries. You are definitely know about the famous lithium-ion battery, and as well as metal air batteries. For instance, lithium air, magnesium air, cadmium air, aluminum, and zinc air batteries. And the third category are the flow batteries, which uh, you can redox battery and hybrid battery are the two typical form of flow batteries. So when you're comparing the metal battery to other battery and energy storage technologies, the first thing that catch eyes is that they are very economic, and the chemical cost of energy storage in metal batteries are very lower than the other uh, battery systems. One of the reason can be this, that metal batteries are using ambient air from the outside as their cathode. So once air is free, then it eliminates the cost of one electrode, and this way you can reduce the total battery, as well as you can increase the total energy density of the battery. So also, when you look at the left down graph, it shows that zinc air battery is having higher energy density compared to lithium ion, lithium cadmium, lead acid, and many other type of batteries. And from the graph on the right, you can compare the different aspects of zinc air battery and compare it to iron air, magnesium air, and aluminum air batteries. And you can see that in all aspects, it is fairly acceptable and comparable. For zinc air battery as you compare to others. Like, uh, for example, in terms of electric potential, maybe it is not very comparable to magnesium air, but in terms of kinetics and reversibility, it is higher than the other candidates. And from the top graphs, you can also see how zinc stands in comparison to the other electroactive metals that use an aqueous or non-aqueous electrochemical batteries, and it stands fairly good with high energy density, specific energy, and all other properties. Um, Looking briefly into the history, the first zinc battery was invented in 1878, and the progress of zinc battery has been continuously going on until in 1998 the electrode additive was introduced to zinc air batteries. But you may notice from this graph that from the years of 1998 to 2015, less attention has been paid to zinc air batteries, and rather more concentration of research has been focused on using lithium air batteries. But in 2015, with the introduction of gel polymer solid state electrolyte for flexible zinc air batteries, the research the interest has been attracted to from the researchers more towards the zinc air battery. And as it going on, different configuration and aspects of zinc air battery has been uh, involved in the focus of many researchers, and it is yet still going on as a hot topic. So moving towards introducing zinc air batteries, they are having a theoretical voltage of 1.65 volts, but in practice, due to a number of reasons, their OCV is usually practically about 1.35 to 1.40 volts. This can be due to the sluggish kinetic of oxygen reduction reaction, which I will be explained shortly. So, as I stated earlier, zinc air batteries are using air cathode, which allows the oxygen from the ambient air to penetrate through a porous structure of air cathode into the system. And the air cathode is usually consists of two layers of gas layer, which is located at the outer surface, and the catalyst layer, which is located at the inner surface. So once the oxygen molecule passes through this air cathode, it converts to a hydroxide ion, and therefore the hydroxide ion can be consumed in a battery to make to generate the reactions with the anode. So these are the typical reactions that in rechargeable zinc air battery can be occurred. So as in the anodic side, um, zinc reacts with hydroxide ions to form zincate ion and liberates uh, electron. and the zinc cation later in the electrolyte dissolve and converts into zinc oxide. On the cathode side, however, uh, the oxygen molecule from the air will react with water and also will accept the liberated uh, electron from the anodic reactions to form up the hydroxide ion. So the overall reaction for this battery is zinc plus oxygen forms up zinc oxide. The chemistry involved in zinc batteries reminding us slightly similar to the hydrogen fuel cell. And for this reason, many researchers are adapting some ideas and materials that have been used in hydrogen fuel cell and investigate their applications in the zinc batteries. Uh, Considering these uh, zinc batteries, um, we know that the commercially available types are only the primary batteries, not the rechargeable batteries, at least to this moment, uh, as far as I have knowledge on. And this is due to some difficulties that the zinc batteries are facing when they are applying in as a rechargeable battery. Uh, for example, during the charging, uh, when you try to increase the voltage, you may accidentally generate hydrogen gas instead of zinc. So, because the reduction potential of hydrogen is very close to zinc, and also for zinc have lower reduction potential than hydrogen. So, uh, sometimes you ended up making a lot of generating a lot of hydrogen gas instead of zinc, and you're losing performance through the HER or hydrogen evolution reaction. The second is the degradation of air cathode, especially during charging. As I stated earlier, we generate oxygen bubbles, and this oxygen gas can sometimes uh, involve in a reaction with the cathode material in the air electrode and form up the carbon dioxide, which, especially during cycling, this reaction will end up destroying the air cathode and degrading it and make the shelf life of the battery limited based on this. The third is that you may end up producing hydrogen peroxide rather than water. So through a two-electron pathway reaction, the hydroxide ion may turns to hydrogen peroxide, and rather than four-electron pathway reaction that will ended up generating water molecules. The fourth problem is related to as the zinc battery should be exposed to the air or have access to the air. So there is a probability that the hydroxide ion inside the battery react with the carbon dioxide from the air to form carbonate, and this carbonate can cause some issues, including it uses the hydroxide ion and deplete the concentration of hydroxide ion in the battery, which is very uh, significant element in terms of the reaction kinetics. The other thing is that this carbonate material is insoluble in the alkaline electrolyte, so that it could be precipitated in the battery. And the other is that the third is that it changes the pH of the electrolyte, and it will decrease the electrolyte, and so the reaction and the performance of the battery will be affected as a result. So I mentioned the sluggish kinetics of ORR uh, in from the air cathode, and this graph shows better how the large over potential of the ORR reaction can result in a lower, significantly not significantly, but uh, quite lower uh, battery voltage, less than 1.65 in practice. So To conclude this advantage and disadvantages of zinc battery, we can mention that the higher energy density, flat discharge voltage, they're not toxic, at least based on the metal element, and they are very inexpensive. But for disadvantages, we should highlight the limiting power output as regard to HER that I explained earlier, and the limited shelf life that can be due to many aspects of cathodic and anodic, and I will explain this further on. And also the operating temperature range is limited because this is an aqueous battery, and while if the temperature is very high, then we may lose the water content from the system. So basically, when talking about commercialization of zinc batteries, the two important things will come to the mind with what is the problem regarding the air cathode, as I explained earlier, and but the most important one I believe is the zinc anode problem, which by itself can be categorized into passivation, zinc corrosion, and dendritic growth of zinc. And this graph shows it very clearly how these three issue will affect the surface morphology, the surface of this zinc anode. Like here on the left, this is a growth of dendrite, and in the center is the shape change of the battery that it can be occurred during the cycling, and on the right side, it is the zinc oxide that has been deposited on the surface and passivate the surface. And on the last bar, you can see the hydrogen, how hydrogen can corrode the zinc. So in order to explain further about these anodic related issues, I'm interested to introduce a published paper which has been published a few months ago with the title Stabilizing Zinc Anode for Different Configuration of Rechargeable Zinc Batteries. So in the paper, uh, we were trying to explain and categorize the solutions that has been addressed to overcome the anode-related issues in rechargeable zinc battery, mainly categorizing these solutions into operational-based solutions, uh, material-based solutions, and cell architectural-based solutions. So, for beginning, we start with cell architectural-based solution, which are mostly highlight the solutions that has been used different cell design and configuration to overcome this anodic issue, like introducing flow batteries or using different orientation of the cell. Some instances of our flow battery system, cell oriented vertical or horizontal, using planar or tubular cell, or using multi-stack cell instead of a single cell. And regarding these issues are mostly highlighted the evolution of each of these cell configuration on the zinc morphology on the zinc anode. And it is here mentioned that when you're using conventional planar zinc battery with stagnant electrolyte, your zinc morphology will likely be filamentous and mossy. So to better imagine how it would be look like, the last two morphological images are uh, semi-spongy or mossy and flammless. So they are loose zinc particle that not very good uh, addition to the surface. And for the flow electrolyte system, the, the it facilitates the growth of adhesive deposit with flat or compact morphology. So when we're using flow system, our morphology will more likely to be like a boulder shape or layer shape, but it is very compact and dense. And when we're using multi-cell zinc batteries, so The smooth morphology is very preferable, and it should not be dendritic. So as you can see, any cell configuration we use will require some specific ideal morphology for our operations. Okay. The first thing is the introducing of flowing electrolyte. The first advantage it gave us is that the high depth of discharge is feasible with flow battery, which means that the bulk of their nominal capacity can be discharged without causing long-term damage to the cell. And also, we know that the electrolyte momentum can balance the ionic composition and also regulate the current density in a diffusion layer. So in that case, the morphology will be uh, smooth when using uh, uh, the momentum of electrolyte, circulating electrolyte. And also some insoluble precipitates can be also swept away and carry away with the electrolyte and discharged from the system. So a continuous supply of fresh electrolyte to the cell improve both charge and discharge efficiency and eliminate side reaction and byproducts. Also lowers the ohmic resistance of the cell. But there are also some negative aspects when using the flowing electrolyte system, which is that the internal pressure of the cell will be increased due to uh, the pressure that indices from the flowing electrolyte, which in some cases can end up with the failure of their electrode, and also the clogging caused by side byproducts and unreacted zinc. So since the electrolyte can also sometimes carry some solid particles with itself, it can cause clogging. So flow batteries are usually in these three typical forms. Maybe there are these two forms, and in comparison with the stagnant zinc battery, in which the zinc is uh, deposited and placed on the surface of the anode, and the electrolyte is not moving, so it's a stagnant system. But when you compare it with hybrid flow batteries, we know that the electrolyte is reserved in the electrolyte storage tank, and with the help of a hydraulic pump, it will go through the system. And once it exposed to the electrode are exposed to the electrolyte, the zinc will be deposited on the surface to the amount of desirable uh, uh, storage. So it is very controllable, makes it very easy for us. And the other type is semi-solid zinc fuel cells. So in this kind of system, the regenerative unit is separated from the fuel cell. So once the electrolyte uh, introduced to the fuel cell and the zinc particles are generated, then they can go to regenerating. Uh, I mean, the zinc has been dissolved in electrolyte, so in the regenerative unit, they can be reduced back to zinc pellets and separate, and the fresh electrolyte will again go through the fuel system. So in general, comparing the flowing electrolyte and stagnant electrolyte system of zinc battery, we can highlight some advantages and disadvantages. Like when we're using flow, the energy and power density are decoupled. Also, we can operate it higher depth charge. The morphology of zinc will be compact and dense, and the passivation layer also have less effect, can affect the system less when the electrolyte is flowing. So the battery has longer durability, but the negative aspects are that they usually are suitable for large scale plant and they cannot be applied in portable uh, batteries and devices. And also, they have reduced energy efficiency. And okay, so jumping into different cell orientation like horizontal or vertical. Uh, the main thing to highlight here is the effect of drag force and gravity. So when when the electrode is oriented vertically, the heavier precipitates can fall down and remove from the electrode surface, while in the uh, planar horizontal type, they will be accumulated on the surface of the electrode. So different product of zinc kit will be resulted when using uh, horizontal or vertical cells, electrodes. The other configuration is the multi-stack zinc batteries. So zinc air cells can be stacked together to form a single uh, zinc air multi-stack battery, and the 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 configuration to fabricate this multi-stack. So the configuration of placing the cells together beside each other can be monopolar or regarding monopolar or bipolar configuration. So the only difference between these two is that in monopolar, there's only one air cathode in contact with one side of the zinc uh, anode, and then they're using of external connection, the cells are connected to each other. Meanwhile, in bipolar, uh, each zinc anode is been faced in two double side with the air cathode, so the current can go through the air cathode throughout the cell. So actually, with using bipolar, you don't need external connection anymore. But the downside and the drawback of it is that your air cathode should be conductive enough to pass the current. Okay, moving to material-based strategies used to eliminate the anode issues. They're mostly focusing on four different aspects. One is to prevent dendritic zinc deposition, also to eliminate the passivation, shape to prevent shape change, and also to prevent corrosion and the corrosion as a matter of hydrogen evolution reaction. So for the to prevent the dendrite, you can either modify your zinc surface, for example, using instead of using a solid um, and smooth surface, you can apply a 3D zinc sponge or using zinc powder instead, or apply some surface etches and modifications, etching and modifications. Um, Also, you can use additives to electrolyte and electrode and separator like PEI, coating your zinc powder with aluminum oxide, with sodium dolityl sulfide, and to the electrolyte, and this kind of strategies. Next is how to mitigate the impact of passivation. So you can either choose different anode material, uh, different metal for anode material, or change the composition of the electrolyte. For example, you can use semi-solid electrolyte instead, or using zinc polyethylene glycol, or uh, silicon oxide, and many other examples are available in the literature focusing on reducing the impact of passivation. Also, you can use additive to the electrolyte like potassium persulfate, DMSO, or even room temperature ionic liquids can be helpful. The third is the shape change. So, in order to prevent the shape change, which usually happening during the cycling, and when it's it happens as a redistribution of zinc when you discharge zinc and it dissolved into the electrolyte. By the time you are going to charge back, it will not deposit at the very same uh, area. So it will either sometimes accumulate at some spot and making a deformation to the surface of the anode. So to avoid that, you can use additive for your electrode or electrolyte, like using potassium fluoride or potassium carbonate, or you can just make some improvement to the electrode, like coating zinc by AEI, or lower the uh, KOH content in electrolyte and decrease the pH. Can also help in that case. The, the last category is the corrosion, which is a very uh, important thing when using alkaline batteries. So to prevent the corrosion, you can apply alloying or coating of your electrode, or using additive metals such as cadmium, indium, or mercury, nickel, and lead. The other strategies, coatings in particles with protective nanoparticles. Or sometimes you can use the corrosion inhibitors, like uh, for electrode additive. You can use activated carbon, acetylene black, graphite as a electrode material, or metal oxide, salts, and some organic inhibitor to prevent the corrosion. But once you're selecting an electrolyte additive for no, or the additive for electrolyte or electrode, you must notice that this material can also increase the battery's resistance and lower the power density. So this might be a point to mention, to remember. And the third main category is the operational based strategies, in which the process operation and process factors are optimized in order to mitigate the anode related issues. Like zincate ion concentration, which is which affects the morphology of zinc, and also optimizing the speed of the velocity of the fluid, circulating fluid, and also the optimizing the temperature, like temperature also the operating temperature. It is very effective, effectively changes the rate of ion diffusion, uh, zinc ion diffusion, and altering the surface morphology of deposition by reducing the size of zinc particle. It also, uh, the high temperature will increase the kinetics of zinc and affect the morphology. And the last one is the current density. So increasing current density promotes ion migration, increases the number of activated ions, and elevates the energy of an atom. At high current densities, diffusion control deposition predominates. The deposition morphology at high current density are boulder-like or dendritic. The morphology of zinc deposit at low current density is uniform, filamentous, and mossy due to 2D nucleation followed by creation of protrusions across a broad platform and inhibition of microstep growth in a lateral direction. Some literature are also using the pulse charging to eliminate the uh, some issues like dendritic morphology, so that the reverse potential in pulse charging can help the zincate to diffuse back to the negative electrode, and therefore reduce the concentration polarization induced by charging. So the final part of the paper focus on mechanically rechargeable zinc batteries. They are typically in two forms of reconstructible cells, in which you physically remove or place back the zinc anode, and also the refuelable cell, in which you can with a hydraulic pump you can flow uh, and feed the electrolyte back to the system. So these fuel cells have some properties like the stores the electroactive component in a tank located outside the battery structure. And also they offer greater flexibility in terms of energy and power decoupling than lithium-ion batteries. And also in order to produce zinc pellet in zinc regenerator, dendritic morphology is preferred. So for this kind of technology, it is preferred to produce dendritic morphology because in a regeneration unit, you're going to more easily separate them, separate the zinc pellets. And also, zinc oxide can be retrieved and converted back to zinc metal via an individual process. And also, the zinc slurry is composed of zinc particles suspending in alkaline electrolyte stabilized with a binder. So this is usually the electrolyte that has been used for zinc fuel cells. There are some advanced commercialized zinc fuel cell technology and with different idea of operation like this on the left this fuel cell developed by Easing company is using the charge electrode on the top side to uh, regenerate the zinc metals, and the zinc metal will at the effect of gravity will fall down to the bottom chamber in which the discharge electrodes are present, and they dissolve back to the electrolyte in during the discharging, and then during due to the concentration gradient they will move up again to the top section. Or the one on the right is showing a regenerative fuel cell system developed by Zinc 8 company, in which the zinc generator, storage tank, and fuel cell unit is separated. So this device is portable and can be located at any sites. Uh, so I'm going to introduce you to the second paper, research paper. In this paper, parameter of optimization was used to see the effect of operating parameter on the zinc airflow battery. For this research, a tubular type zinc battery was used with a tri-electrode configuration, and a brass rod as an anode current collector was installed inside the tube. And for the air cathode, a manganese oxide based catalyst was used, and the gas diffusion layer, in which the composition of each layer you can find out in a table. So basically, we have a hydraulic peristaltic pump here and a electrolyte tank to circulate the electrolyte within the cell. To evaluate the optimization and to evaluate the battery was charged and discharged while a different flow rate, current density, and electrolyte concentration and electrolyte temperature within the range that you can see in the table has been applied. And as a result, the Coulombic efficiency of charge, Coulombic efficiency of discharge, and also the overpotential of charge and the overpotential of discharge has been measured. So while varying the different values of this operating parameter, you can see that, for example, for current density, in case you increase it and see the effect of this increment on the Coulombic efficiency of charge, you can see that it will reduce it. Uh, but you increase the flow rate, you can see that it can generally improve the Coulombic efficiency as it increased. The paper also dedicates some results uh, regarding the morphology of zinc as different flow rate and current density has been applied to the system. For example, if you can look through this graph on the right, you can see that when low current density has been applied uh, in integration with low flow rate, the morphology is quite mossy and loose. But when you increase the flow rate at lower current density, you can see a very smooth surface here. And the combination of high current and high flow also gives a very good morphology with high adhesion to the surface and less dendritic as compared to low current density. The paper also discussed the effect of gravity on the morphology, as you can see in most cases, either by changing the flow rate and current density, but mo- uh, mostly in all cases you can see that the deposition thickness on the bottom of the rod is thinner than the top of the rod. And except for when we use high current and high uh, flow rate. So this morphology here are indicating the one on the top right on the previous figure. And the paper also tried to optimize the round trip efficiency of the system, uh, while the optimal value are incorporated into the operation of the zinc battery. So moving from the papers, we still know that the scale-up and commercialization of zinc batteries are limited with many aspects that we need to consider, like the power demand, battery management, durability, and adaptation. And on the left, you can see the commercially available type of primary zinc batteries in the market that are exist in the market at this moment. So to summarize my presentation, we have investigated the different aspects of operation or material or either the cell configuration, the different uh, uh, amount of each or the different type of each, how can be affected on stabilizing the zinc anode for longer durability, and as well as we introduced the metal batteries and compare with other sources, and also we have introduced a paper that uh, tried to optimize the parameters, operating parameters, in order to increase the performance and the efficiency of the zinc batteries. So thank you very much. This is all about my presentation. So in case there is any question, I'll be happy to answer.
Thank you very much, Dr. Ramin. So, do we have any question from the audience? Of course, you can type your question in the chat box. We will address it. Or if you want, well, if you want to use your microphone or you want to come to the stage, it's okay. Yeah, you can, yeah, notify. Yeah, we got one question from the chat box.
Okay, is zinc battery environmentally friendly? Um, Actually, in terms of the metal base using the zinc battery, it is intoxic. So the, the only concern is regarding the recyclability of the catalyst material and also using the high concentration alkaline, which are not a big concern to the environment, but are big concern regarding the recyclability of the battery. So, and zinc is very abundant, so it's a material that is safe to handle and it's very abundant.
Okay, you mean cyclability, right?
Yes,
Not
the
recyclability.
recyclability. Yes,
Cyclability.
that's right.
Okay, yeah. Because in terms of, well, recycle, I think this one it's one of the, what's it? Zinc it's the material that we can 100% recycle using existing technology, right?
That is correct. Yes.
Yeah. Mm-hmm. but maybe it's not currently, maybe it's not what's it, economic viable because zinc is really cheap.
Yes, yes.
Okay, so we have one question from Professor Ahmad Asmin asking about the air cathode. Comments on the air cathode. What is the best material now?
Actually, for zinc battery, the air cathode is usually a we need a porous structure of carbon, usually carbon material doped with transition metals or sometimes transition metal oxide like manganese oxide, or sometimes we can use cobalt or nickel or iron dope on the structure of carbon in order to fabricate a air cathode. But it should be conductive enough, and also we need to consider that the gas diffusion layer should be hydrophobic in order to save the water content of the system.
Yeah, I can give more information on the regarding the air cathode for for the charging electrode. Well, for the charging electrode first, of course, metal oxide. Now, currently, well, if you look at the commercial system, well, they use manganese oxide. Mhm. Of course, even cobalt oxide works better, but we use manganese oxide because it's much cheaper than other material, yeah, other metal oxide. But of course, we have to control the morphology and also phase of the manganese oxide. Mhm. Yeah, and of course, well, if you want to make it rechargeable, of course, we need a charging electrode, which we need a OER catalyst. In that case, maybe it's we require different configuration of the electrode because for charging electrode dealing with OER, it's quite stability is the main problem. Hmm. Yeah.
Yes.
Okay. Yes. And we also have question regarding pH problems. Can you?
How is
Yeah.
pH problem solved? Uh, I, I'm trying to understand a question. Oh, what is the effect of pH in zinc battery? Actually, uh, the reaction of zinc in uh, high concentrated alkaline is faster. The kinetic is faster, but and because the concentration of hydroxide ion is the important things to be present in a system, and so highly concentrated electrolyte with high pH level will be more preferable in zinc batteries. But regarding pH problem, how is the pH problem solved? You mean uh, the lower upper limit, or I don't understand this question very well.
Yeah. Because pH actually is not a problem. We use very very strong alkali, of course, because in order to accelerate the OR reaction, oxygen reduction reaction, we need very high concentration of potassium hydroxide. Yeah, we have problem on the what's it, corrosion, or corrosion of other metal, but that is we need trade off, right? Mm-hmm.
Yes, I think it is also mentioned in the next question regarding the magnesium and aluminum, because the corrosion of magnesium and aluminum are very high, higher than zinc and alkaline, but they are extremely reactive. But I think the issue about them is that they are not very reversible. So for rechargeable battery, they are not suitable candidate to use. And the
Mm-hmm.
zinc air battery are more preferable in this matter.
Yes. Yes. Yeah. In terms of energy density, of course, because aluminum and magnesium is very light, it has very low density. So in
Mhm.
that case, yeah, energy density becomes very high.
Of course,
Yeah,
this is very
right.
related to the density of the metal. So if the battery has a lower, the weight of the battery is lower, means that you can store amount an amount of energy in a lower, per gram of the material, per gram of the battery. And if your battery is lighter, then
Mhm.
of course the energy density will be higher.
Yes, and because this thing was it, we usually in thin air we can use aqueous electrolyte, but for magnesium and aluminum, no, we cannot recharge it using aqueous electrolyte.
That's correct. Yes.
We have more questions from the floor, from the audience, Ramin.
Ah, I didn't notice. Sorry. Zinc battery. Thanks for information. Zinc battery or lithium ion? Which one is more toxic? Material, toxic of material or electrolyte? Uh, the electrolyte in zinc batteries, uh, we cannot consider toxic. It is, but neither does the lithium-ion battery, if I'm not wrong. Uh,
For,
so
for
the
lithium ion battery, they use non-aqueous electrolyte, they use polycarbonate. Yeah, it's very toxic, of course.
okay,
Hmm. And also flammable. Yeah, flammable and toxic. But in case of zinc air battery, in terms of electrolyte, we use aqueous electrolyte. Aqueous, of course, it's not toxic
toxic.
at all and not flammable. Okay, that's the point. Yeah. Also on the fabrication, also. Mhm. The fabrication of a lithium-ion battery use a very toxic solvent, mhm, much toxic solvent than what we use in fabrication of zinc-air battery. Mhm. Do we have more questions from the audience? Okay. If not, thank you very much, Dr. Ramin.
Thank you.
And well, I hope everyone enjoy his talk today and enjoy our webinar.
Thank you
Okay.
very much for your time.
Thank you. Thank you very much for everyone. Have a good day. Bye
You
bye.
too. Thank you.